Good afternoon, everyone. How you guys doing? Doing okay? Good. So last time we talked about greenhouse gases a bit, talked about Henry's law, and kind of the way we know how gas is going to transport between the gas phase and the liquid phase, partial pressures, all that. Today I want to turn our attention back to, transport process more generally, and that would include, we talked about this a little bit at our first or second lecture, that would include tracking a plume of contaminants or pollution of some sort through water or air, even through groundwater and soil type of stuff. And so you can imagine looking at some picture like this where you have some pollution discharge. Maybe that's Deepwater Horizon oil spill, maybe that's a smokestack in the air. Whatever it is, you see there's different processes that affect it, right? I'm going to leave the math of calculating diffusion, which there's some math we could use for that. If you do so, you get into three-dimensional analyses, and I don't particularly want to get into that with you guys. But suffice it to say, we've got advection here. So that's the physical moving, as I've told you in the past. We have dispersion and diffusion, where diffusion is random molecular motion, and dispersion occurs when you have perhaps some eddy flow and it transports stuff in a little bit of a random way other than just straight advection from point A to point B in that one direction, right? Dispersion is still sort of advection, but it's a little bit more random where you end up. So it's, in a way, dispersion is somewhere between the two. And what I want to do today is use this topic to lead us into reactors, which is a major component of air or water treatment. We're going to use reactors of some sort to implement some change to the pollution, right? When we first started talking about environmental systems, we can think of some volume containing some stuff, and a lot of times we'll send it through some sort of reaction. Something's going to happen, and then we get maybe just the stuff was destroyed, or maybe that stuff is now in a separate pile where we can landfill it. Some process, right? We're going to send it through some process, do some sort of reaction. So what I want to lead us to is how do we understand the flow, and ultimately next time we'll get into reactions themselves, what happens in there, and how do we mathematically model that. We've already talked about it a little bit when we introduced the fundamentals of mass balance, right? We've got flow going in, flow going out, something happening in the middle. Our mass balance systems are, what we've seen so far, are pretty simple. And so next time we're going to add these reaction components. And this time what we're going to do is take a look at how water or how air is going to flow through a given reactor and what that looks like in practice. So we're going to start with talking about flow in a porous media. So when I say porous, I mean, maybe it's some column that's packed with little beads everywhere, and water can trickle its way through, find its way through the pores, the spaces between particles. That is a very fitting description of soil as well, or most soils. You can think of sand. Water can flow pretty readily through sand because they're relatively large grains, and there's spaces between the sand grains, so it sinks right through. Whereas if you have a clay or some thick sediment that's just really densely packed with very tiny particles, it takes a long time for the water to go through that, right? So when we think of flow through some sort of a porous media, you think to yourself, well, the water, if it's flowing through, is going to have to take some crazy path to get there to the end. And if there's stuff inside the water, well, that might get delayed or bounced around, and something may happen to the transport of that stuff that's inside the water as well. It's actually a big field in almost all analytical science, chemistry type stuff, is using chromatography, some way to separate molecules, or in some cases, small objects, based on how they're interacting with a media like that. it's the simple case of chromatography is you've probably done it before in the past. When you're maybe a kid, you have a napkin and you put a lot of marker ink on it, and then you put that in water or ethanol or something, and then you can see the colors start climbing up the wet napkin then as those the ink molecules are separating, and you start seeing different colors other than just like the black ink, because the black ink has different colored molecules in it. They're traveling and they're encountering somewhat of a porous media in some sense. The water is able to travel through the napkin, through the paper towel, whatever it is, and some of the molecules get slowed down in that process, even though the water you can see is traveling through. And then you can see how maybe the red ink travels the furthest, and then there's the blue or something like that. So you've probably seen that before. So when we talk about flow through porous media, or understanding transport through porous media, this is where we can talk about, again, dispersion, advection, and diffusion. I want to highlight dispersion in this slide. So if we imagine we have some column, so we've got some sort of system where we've got a water and tracer input, and it's going to go through here. The flow, as we see, is going downwards. I guess we've got some little overflow thing. We can ignore that. So we just got water going through this porous media, and at the bottom, what we're doing is measuring the concentration. We have an initial concentration and a final concentration there. So that's our C and C naught. And what we want to know is, how is this travel through this porous media changing the concentration? Because if nothing happened at all, if it was just a pipe and water was flowing straight through it, we would see this concentration that we added in this little bit of space. It would just be at the full concentration, and we would see that concentration just come straight out. If we plot it, that's this no dispersion case. So this graph here is looking at C divided by C naught. So the fraction, so C over C naught would be the amount that we're measuring divided by the amount that we started with, or that we put in the first place. Okay? So C over C naught, if that's 1, if we are measuring exactly the amount we put in, then all of it has come through. There's no loss, no change, no nothing. So in terms of, if we're continuously adding this concentration, so continuous feed, we start pumping in a bunch of dye, and we keep pumping that same amount of dye in, we expect that we will eventually get, once this column is completely saturated with that dye and everything coming out is at that concentration, that eventually C will equal C naught. It'll be 1, right? This ratio, and that's what we see in this graph, right? No matter what case we look at, it comes up to 1 here. So what we want to consider then is, if nothing weird happens, it's just we put water in, it's got concentration, and we're pumping it in, then we would immediately see that concentration. You see the dotted lines here, and then it jumps straight up. As soon as the water meets the end of it, that profile just jumps up to C over C naught is 1. All of what we put in is coming out now. So maybe we started over here, and it takes 30 seconds for it to come through, then boom, it's all there. Now, that's not reality. In reality, we would have some dispersion. And dispersion would mean that some water is taking a more direct route, whereas some water, and the particles in that water, are taking more of a circuitous route, and finally reaching the end. And so that process, that dispersion, is going to cause some of the stuff to come out early, as we see here, and some of it is coming out later. And around the time where, if no dispersion was happening, that's probably about the halfway point. Half the stuff has come through. And this profile might look, depending on how long the column is, depending on how much dispersion is happening, maybe it looks a little bit wider, something like that, or more sharp. It just depends on kind of the system right there. And actually, we can, if we wanted to, quantify how close to an ideal plug flow reactor. We'll learn more about that in a few minutes, how close to that ideal reactor that we can model it is based on how far that tail is or how short it is. So that's the dispersion case. There's another thing that we could consider if, in addition to just dispersing the flow throughout, we are also slowing stuff down. So if we've got a molecule in there that likes to stick to the media, then that molecule is going to kind of slow down, stick, and I mean, eventually the sticky sites will get used up, or it'll just desorb back into solution, and they'll just slowly make their way through. This is that chromatography example. Some molecules are being slowed by the material that's in the napkin, for example. And so if stuff's getting slowed down, then water is flowing through this whole time, but the tracer that we added there gets slowed down significantly past when the water that we added is coming out, because that's coming out around here. And then the molecules then start coming out and have a similar profile there. So that's what we might call retardation in that process. So we often make use of that. We need to understand that if we're going to design, let's say, a groundwater treatment operation. How slowly are these things going to make it through the groundwater? And we'll see an example of that in a minute. Okay, so that's dispersion, and then this retardation part, really that's generally caused by adsorption, which is another process that sometimes we'll use intentionally for treatment. Activated carbon, if you've ever used a Brita filter at home, essentially what you're doing is an adsorption process. Whatever molecules that might be hanging around in the water, you're wanting them to stick onto the surface here, and while they might one day eventually come back out, especially if you saturate it, the idea is it's got a lot of space, that activated carbon stuff, a lot of space for molecules to stick to it, and we'll remove it that way. And then you could replace it, every once in a while, and you'd be good. Okay, so another look at this, if we take a look at diffusion, what diffusion is going to look like is, instead of adding like a continuous feed, well, we'll talk about continuous in a moment, but if we added just a spot, and again, that napkin example, if we put some ink on a spot and then allowed the molecules to diffuse, we would see, our initial time point is just one little dot here, and then over time, we'll see the concentration expanding outward pretty much uniformly in random directions, giving us a nice little circle here, and on as time goes on. So that's very simple, the diffusion from just like one spot kind of a thing. And we would expect this to happen in just about any system. So when we talk about ideal reactors, this is something we often assume is not going on in certain cases. Obviously, that's not a realistic assumption, but if we design our reactors and then add in some factor to deal with that non-realistic component, but we can do the math on the ideal scenario where there's no diffusion, that can actually simplify things and let us have a better hold of the mass transport in a given system. So that's kind of what we'll take. I wanted to introduce you to these concepts so you're kind of familiar with what might happen if we go away from our standard or ideal systems. Okay, if we had a continuous input into some system, here we're looking at the C over C naught again, so the portion that has come through, and we're transporting this stuff along some axis, then one thing we could take a look at is if we add the tracer, so T naught, here we have C over C naught is 1, so we've got everything we've got is coming through, or we're measuring it right there. If we take a look as, let's say we started with I should have brought the caption for this figure, actually. I'm trying to think of what this is exactly depicting. So we've got the direction of transport there. I think what it's showing is if you're tracking the center of a plume, or like if you're tracking this dot, but then you're also, that dot is moving along through the groundwater or through water or whatever, and diffusion is acting on it, what you're going to see is initially you have everything's in that one little dot. And then sometime later, not everything, but most of it's still in that dot position, but then you also have some concentration out over to the side. So this is kind of matching up here, right? So it's sort of like a concentration profile versus like looking at it top down. And so if you're looking at how concentrated it is, or how much stuff is, I don't know, 5 feet away versus within the couple inches right there, you'll see this profile. So that's just what it's drawing. And so we can see how the concentration profile, after some time, this diffusion is going to cause it to spread out. So that might mean that if you're transporting this in some direction from left to right, then some of the molecules are actually diffusing backwards, right? So even though the flow is going to the right, some of the diffusion is causing molecules to go left. Some diffusion is causing it to go right. And so you get some molecules that speed up and some that are slowing down compared to the direction of the advection, the flow. Okay, so that's what this is indicating here with this graphic. Okay, so with that, we can say that even if we know the flow of something, we also probably need to know the diffusion. That's going to depend on how big the particles or molecules are, and the temperature of the water, how viscous the water is. For it to do that in honey, it's very viscous. Particles aren't going to be able to diffuse quite as fast. So there's a lot of things that would go into that, certainly things that we can do, and I'm going to leave most of that for your groundwater classes and other classes you'll take. Okay, but I do want to focus in a little more on groundwater, introduce you to the concepts, how they will be used once you are dealing with those. So if you just put a pulse, so that last time it was kind of considering, actually I don't even know, that might have been a pulsed input. But let's say you're taking a look at groundwater and you have some contamination that just happens, right? Oil spill, something, underground storage tank that leaks and then it's fixed, but that pollutant is still there. You've got that input. So if you had it released at some, at we'll call the point of release distance is 0, that's our 0 point. And then you have 2 meters away some monitoring well. So you're checking around this point of pollution, are you detecting that pollutant? That's a pretty common thing to do, is check every few meters, every so often. Are we seeing this contamination that we know is there? Is it traveling this way? Is it traveling that way? How fast is it? We have to do a lot of groundwater monitoring for that type of application. So in this case, what we might see is over time, we have some concentration that is essentially, if the groundwater flow is flowing this direction, we expect to see the contaminant to come out in this monitoring well. And so this second component of the graph is monitoring it, saying, okay, at some time, we see the concentration coming out, right? That's what this graph is showing us. So we're essentially mapping how long it takes for the contamination to travel. In this case, we have a non-sorbing contaminant or compound. And so what that's meaning is it's not adsorbing onto the soil particles. It's not sticking to stuff. It's not being delayed by that process. And so if we have non-sorbing compounds, maybe in this case, after about 8 days, we get most of the stuff coming out. If we have what we might call linear adsorption, so adsorption is pretty, there's a couple ways it can occur. We'll just leave it at that. So linear adsorption, we see it slow down a bit. And then this nonlinear adsorption, maybe it's really, really sticky and it's sticking so much that it takes a very long time before we see any of it. And then we're just only getting a little bit of stuff coming out for a long time. It's kind of the worst case scenario in some way because it's harder to pump all that out if it's going to take days or years for it to actually travel through and come out of the ground. So then we might have to look into other options to do the treatment in the ground, in situ, instead of just pumping it out and treating it as we pump it. Okay, so here's an example of contaminant travel. Again, that marker and napkin example. Maybe I should have brought a demonstration with me. I didn't even think about that example when I was preparing this, but it fits. So in this case, we have 3 different contaminants that were released at the same spot, and after some number of days, I think those 21 months, so we had a contamination input right there at 0, 0, and 21 months later, these were measured to see, okay, how much contamination are in these areas. And this is probably captured using a series of wells in a lot of different places. So the axes are meters, so they probably have monitoring wells in kind of a grid or in some type of a grid form to estimate these the concentrations in these plumes. And so, in fact, that is a pretty costly endeavor to put that many groundwater monitoring wells in, and to monitor them over time. Groundwater contamination is costly in that manner, even just to track it, whether or not you're actively doing cleanup. So we have these 3 different compounds. The Cl here, that's just chloride, Cl minus. The Ctet, that's carbon tetrachloride, this guy. And then PCE, that's tetrachloroethylene. So it's pretty common dry cleaning contaminants here. So if we take a look at how they traveled, how far they traveled, given that the groundwater flow seems to be kind of in that direction, what we see is the chloride traveled pretty far. That's 40 to 60 meters, I guess, in the X direction, and which this one is X for some reason, and 20 to 40 meters in the Y direction, something like that. And so we can say, oh, this traveled that far. Now, chloride, being a charged compound, Cl minus, that's not likely to be reacting with stuff. In fact, all of these are not very reactive, which is part of the reason why they're a problem. Cl minus is not necessarily a big problem in general, but it's a good tracer to see, okay, if we have some elevated amount that was part of this contamination, it would probably be easy to detect that we have an elevated chloride concentration. So Cl minus is not necessarily, it's probably not going to stick to soil particles because it's happy to be in water. Whereas these other molecules are not as polar, so Cl minus is just a charged ion. These guys are more likely to stick to organic compounds, just their nature, and so they're probably going to be sticking to the soil particles and the molecules within the soil and be slowed down. And if we take a look, we see exactly that. It turns out that the Ctet travels a bit further. We can kind of see these lines here estimating it's almost like a topographic map where the highest concentration would be the innermost circle, and we kind of estimate how wide this plume is going and what concentrations are in it. And we see the dispersion and diffusion happening here, right? We can see it's kind of traveling outwards in each direction. And this PCE really doesn't travel so far. It seems to be lagged quite a bit. It's maybe that area. And so we can see that in action, right? So these principles, you'll learn a bit more about them taking soils and hydrology, all that. But it's essentially this mass transport, right? So again, this principle is going to come back at you pretty much every course in some manner. Where's the mass moving? How fast is it going? How can we track that? Last thing, what I'll say is the way you can treat groundwater is typically, one of the common ways is to pump the pump the groundwater out, and you'll cause a cone of depression. So here what we're looking at is kind of an aerial view where we have a pump here. If we were looking at it from like a side view, like a cutoff, we might have the soil here, some groundwater, and then the pump is making some cone of depression here where we're drawing down the water, and it's essentially pulling water nearby into this pump. And this would be, you could draw this as a 360 circle if we were to add a dimension there. Right now, we're just sort of looking at it straight on. But the point is it's drawing down the groundwater and it's pulling stuff from around it, and that's what this graph is showing, is the streamlines here. This is showing that the groundwater is generally moving this way, and then these streamlines are showing as this pump is depressing that, that groundwater there, it's causing there to be a gradient, and it's sort of pulling stuff in, right? So that's kind of showing that effect. You can think of this as like a little whirlpool, right? It's pulling stuff all around, and it's like this spot is literally lower in the ground. The water table there is literally lower than in the surroundings, so the water is sort of flowing downwards into it. And of course, if the groundwater is flowing this way, then that says something about, okay, we can kind of stop the flow here. The groundwater really isn't flowing. The groundwater here was still sort of flowing that way because it was going to be anyway. The groundwater way out here is probably not affected. And you can just sort of map it out that way based on the pumping rate and the groundwater flow rate and all that. So anything within this barrier here is going to be captured. It's going to be pulled into the well and out, and then anything that's outside of that capture zone will be out of the way. So again, it's very important to be able to understand where stuff is going, how far it's going to diffuse to the side. If we had a spill over here, how much of it is going to make its way outside of the capture zone before it all gets pulled into the pump there. All right, so with that, I want to shift our focus a little bit to reactors. And in talking about reactors, I want to make this connection where we were talking about adding some contaminant or tracking some contaminant. We can also add a tracer, we mentioned this before, in order to understand where in our system are the contaminants, or is the water even that we're adding, where is it going to end up? How far is it going to go? How fast is it going to go? See a little picture here of somebody doing a tracer test in a river or a stream. And essentially what you see is this dye being added, and it's in this section of the stream. Of course, it looks like there's plenty of stream over this way and on. So he's not perfectly adding it uniformly across this stream here, just to that spot. And presumably they'll be tracking to see how long it takes before this dye reaches some endpoint that maybe they're going to see the flow dynamics for several kilometers of the stream. So we can do the same thing either to understand environmental systems or to understand our engineered systems to see really how quickly the water is getting through. What's the flow rate like? Is it ideal? Are there channels where this is going to get stuck? What's going to happen there? So we saw showed you a graphic of this, but not probably the video a little bit ago. So if we take a tracer test here, this blue ink was added to this system, and we're essentially just tracking this blue ink as it travels around this bend. So what you'll notice is there are a lot of spots that really it's not quite ideal. So you'll notice up here there's some space where there's clearly should be some water, but the ink is not getting there. There's a little space down here where, again, there's sort of a dead zone where it's just not mixing particularly well. You also see that it's kind of darker over here and thinner, lighter colored in some spots, pretty light right here. And you can already kind of see that this area is probably not going to get much mixing. So this is certainly not an ideal reactor. What we're seeing is different occurrences happen. It took some time before dye reached here, and it would probably take a little while once we stop adding dye for that dye to clear that spot. It's kind of a low flow or a dead zone. So just wanted to show this. I'm going to show a couple more in a minute, partly to remind us what we're talking about when we're dealing with these tracer tests, and also to introduce the concept of what it's like to work with a reactor. So that, we could use that same principle for a stream. If we're going to use a stream and try to understand something about the stream dynamics, we can use it for maybe an indoor air to understand how air is circulating. Maybe we'll use some sort of a gas or smoky particle to track the airflow through a room, see how quickly it's sucked up by our nice filtration unit back there. Maybe it's a drinking water treatment reactor that we're trying to understand how long is the water going to go through and how much UV dose is it going to get before it gets there. In any case, there's three particular types of reactors that we can simplify most systems down to. So we're going to focus on three reactors, and it doesn't matter what's happening inside them. There could be a reaction, maybe there's no reaction. The reaction itself, if there is a reaction, does not depend on the physical shape, right? It could be in my bottle with a reaction happening, or I could dump it on the floor, and the reaction presumably would still be happening if there's some reaction, right? So it's not to do with the physical form. So when we get into it next time with the different reaction types, we got to keep those concepts separate between the physical form of the reactor, how water is going to flow or not flow through it, and the reactions that may or may not be happening inside. So the three basic types are going to be what we'd call a batch system, and we'll focus on each of these in a moment. Batch system, where we have it completely mixed, and if we're assuming it's an ideal reactor, we're assuming that it's perfectly mixed. Every bit of stuff in here is perfectly mixed. So it's what we want if we pour a cup of coffee, we've got some creamer and sugar in it. We want it to be perfectly mixed, right? We don't want just like all the cream to layer at the bottom and the sugar and then have black coffee at the top. That's not so good. And actually, it's interesting, if you do drink coffee, you can take a look at how that mixing is happening in action and how a little bit of wind blowing over the surface can affect that. If you felt like doing that next time, just blow on it. You'll see it actually causes some mixing, just not a lot. Okay, so then we have a Cstr, continuously stirred tank reactor. That's like our batch reactor, except that we've added an inflow and an outflow. So instead of just like a kiddie pool that has just some water sitting in it, maybe this is a more elaborate pool with a hose running in, and there's also having water drain out. You have some input and output. Usually it's going to be larger than just a hose in a swimming pool, but technically that would be a flow-through reactor. Water is flowing through it. You could think of a lake, right? You typically have a stream, especially if you created a dam, right? If you made a dam, you're slowing down the flow from some stream or river or several. You've got a big body of water there, and water is flowing out it, presumably out the other side of the dam. You're just controlling that rate, so you can control how much water's in there. That would be a Cstr if we assume it's perfectly mixed. So this is a case where it's perfectly mixed, like that batch reactor, and we have flow going in and out. The last one is called a plug flow reactor, and this is sort of the inverse of the continuously stirred one, where we're assuming that there's no stirring happening. The good example is a garden hose sitting out in the sun. It's full of water, and you turn it on and you get really hot water. It's been stagnant, it's been sitting there. And it takes a little while before the cold water reaches the end, and then it's nice and cold. It's from whatever's running in your taps and the pipes, probably the temperature underground. So in that case, we assume that in some little segment, it's not mixing from the front ends of the pipe to the back end. Otherwise, it would just be, you'd immediately, as soon as you turn it on, you'd have some cooler water mixing in with it. But no, it's all warm until it all comes out. So that's what we'd consider a plug flow reactor, and we'll get into more of those details in a moment. So depending on which type you're using, and there's reasons to use both, you can take a look at what happens if you add some tracer. So if we add some material that we can track easily, then in an ideal reactor, again, we have this graph here where we see this concentration as C over C naught. If you did a pulse input at time 0, you added that much, then sometime later, you're going to be able to measure what's coming out. And in a plug flow reactor where you have no mixing through it, you put a bunch in and then you wait one hydraulic residence time, so the amount of time it takes for the water to travel through the hose. We'll talk a little more about that in a minute. Then immediately you measure the same amount that you put out, or that you put in, right? It all comes out all at once right there. However, if you had and that would just be like you put a bunch in and stopped, right? Kind of like that guy dumping a bunch of dye in the river. Just dumps the dye and then watches. So if you do that with a continuously stirred tank reactor, what you're going to have is it's immediately going to get mixed all around. And so you're going to have your initial measurement be, whatever that dilution created, that's going to be your initial measurement. And from there, it's just going to be slowly decreasing as you still have clean water coming in. So you have that clean water in the influent, and you're measuring what's coming out. Turns out that since it's completely mixed, you could be measuring what's coming out, or you could measure what's inside, and it's the same thing. We've got C here and C here. And the C naught was just right when we added it, we measured it, that was C naught. So what's coming out, though, is whatever dilution state it is at. And so we just see that tracer amount decrease over time, and it's not like it's all out by that first hydraulic residence time, because there's still water with some stuff in it. It's just slowly leaking out, being diluted out. So it'll take a little while. Okay, so I wanted to take a look at a couple more videos here. So this one, so very simple. This is a batch reactor. We're just looking at adding some tracer to a reactor vessel here, like a batch reactor vessel, and just kind of watching what happens. So we've got it mixing. And you see it takes a moment. It's not truly perfectly mixed, but after a few moments, it's pretty much perfectly mixed, right? It's pretty simple. This one kind of goes back to our plug flow reactor. If we have some stuff being added, and it's going to flow through this reactor, and in this case, what this one in particular is going to show is if it was not ideal, and there's some diffusion happening. So an ideal one, we would assume no diffusion just to make it easy. But this one's going to be a plug flow, and you can see the diffusion carrying stuff kind of forward and backward as it's moving through. And this is some simulation that somebody made. So as you're watching this, imagine this kind of red segment. That's like a little plug of water that's traveling through. And if there was no diffusion, it would just, that red zone would be kind of just staying there. It would travel all the way through just as that red zone, right? So there'd be nothing else happening. It would just be that plug going through. That's our plug flow reactor. We're treating it as if everything inside that little bit is mixed, but it's not mixing with the neighboring water, okay? In this case, we do see some mixing by diffusion. There's some diffusion that's occurring as that non-ideal case. All right. So if we have a non-ideal case, like we're just looking at, if we check the concentration over time, what we see is a mess. So how much of a mess will determine how ideal or how non-ideal a reactor system is. And it turns out that, if you have, let's say your input and you're measuring in your output, it might be shaped something like this. So in your input addition, if that's not perfect itself, it's not uniform, you got some awkward looking shape, and then even worse, in your output, it might look like something like that. So just kind of giving you a little picture, certainly not something we're going to deal with, but you can really learn a lot from a reactor given a tracer test to show you how long the water is really staying in the system in that manner. Okay, so coming back to our reactors, this is the physical housing of a system that we want to understand or cause some reaction or model some system. So this is going to be typically what we're drawing a control boundary around for some mass balance. It could be this room where if we're doing a mass balance on people, there's 3, maybe 4 potential places for people to go. There's 2 doors there, a door there, and a window here. So you could track, okay, how many people are going in and out of the exits, right? That would be our flow, our inputs and outputs. If you had, something else happening in here, measuring CO2, people are breathing in oxygen, breathing out CO2. You have maybe inputs and outputs through the vents and doors or whatever. You could see how maybe there's some reaction that could slowly change the amount of stuff, amount of CO2. Maybe we're burning a candle and measuring, different things. You could see how some reaction within the room might change that. Could be a disinfection chamber. Okay, you have water contaminated with viruses and bacteria and stuff. It's coming in. You've got a disinfectant treating it. Okay, well, it's reducing it, and then how much is coming out. So these are the system is what we're talking about. We kind of labeled each of these already. What I want to highlight is that accumulation, again, we're coming back to the mass balance principles here. We're going to say that there's some accumulation, maybe this is dc dt, in some volume. And that's going to be equal to the input rate minus the output rates plus whatever reaction rates we might have. Okay, so this might be something like V dc dt, let's say for the Cstr here. Then we have a flow rate Q coming in, a C initial coming in, QC naught, have a Q and a C here, plus some reactions. Okay, so we'll deal with the reaction term later, but what I do want you to recognize here is that reaction term is going to be directly put into our mass balance equation. Okay, when we're trying to understand how much mass exists or where it's going and all that, we need to know how much is being added, how much is being subtracted in our systems. Okay, before we get to each specific reactor type, I want to introduce hydraulic residence time. It's a fairly straightforward concept, probably mentioned it already. It's really a key design parameter for any system where we have a flow going through. So theta, or hydraulic residence time, is simply the volume of some chamber divided by the flow rate through that chamber. This is hydraulic residence time, so time is going to be the units. If we take a look at this, volume divided by flow rate, and flow rate is volume per time. That's going to give us time as a unit, right? So when we do anything with hydraulic residence time, we should commit this to memory, that this is the equation for it. And it makes sense too, because how long is the water going to stay in the hose? Well, it depends on how fast you're pushing the water through, and it depends on how much volume that hose has inside of it. right? If you turn on the spigot and you're doing 1 liter per minute and the hose holds 2 liters, the hydraulic residence time, intuitively, that's going to be 2 minutes. So it's going to spend that amount of time pushing it through. So if I did that right in my mind there. So it's pretty simple. You'll use it a lot for all sorts of reactors. And you can use this, you could use this as a hydraulic residence time. You could use it the same concept for a residence time of air in a room, how many air exchanges. So it's really, that principle is just how much volume and how quickly is the fluid, is the air, is the water going through that system and being changed. You can use this to estimate, or you can use the tracer test we talked about to estimate this, whether you're looking at a stream, a bayou, a lake. You can estimate a hydraulic retention time if you can do a tracer test and track how long it takes for that tracer to come through. And that's exactly what a lot of these concepts we're doing here is trying to understand how long did the water stay in there. So this tau is also hydraulic residence time based, different books, nomenclature here. You could also call it lifetime, in some sense, the lifetime of the water in the reactor. So I just introduced it as theta. But essentially, that's what a lot of these things can give us information-wise. It's really important if you have a non-ideal reactor to get a good estimate. That's probably what you have to do. For ideal reactors, typically we can just say, okay, well, what's our flow rate? And what are the dimensions of a reactor? We'll assume that it's ideal flow, and we're off to the races. We know what our retention time is going to be. Okay, so let's talk a little more in depth about each reactor type. So the simplest case is going to be the batch reactor. And it's simple or simplified because we have no flows in or out. So when we talk about a batch case, the accumulation rate, so in the volume of the chamber here, got some volume, the accumulation rate we would describe as dc dt. What's the concentration? How is that changing in the system over time? And we're going to say that would be equal to in minus out, but there's no in or no out. So those go to 0. Plus whatever reaction's happening. So we'll say plus a growth reaction, or the net growth, maybe there's more than one reaction, minus decay reactions. Just going to abbreviate that. So essentially, it's just growth or decay. Maybe we have bacteria growing in my water. So we could track how quickly they're growing. Maybe there's also bacteria dying in here. So then we need both to understand how much bacteria are going to be in here tomorrow, if I had left it there and drank from it tomorrow. So the point is, in a batch system, our accumulation rate is really just going to be this V dc dt, and that's going to be equal to the reaction, the sum of the reactions. So I'll just write reaction rate. And it turns out that the V's are going to cancel, and it's just going to be a differential equation that tends to be pretty simple. We'll talk more about the different reaction rate orders next time. The worst of it is a little bit of calculus that you will remember when I remind you of it. Okay, so it's not too bad. It's something that, once we review it, you'll be like, oh yeah, I remember that. I had forgotten, but I remember now. We're good. So in this case, the batch reactor is simple that way. And if we wanted to study some reaction rate, turns out that it's very common to use a batch reactor where we have maybe a stir bar in here, we have the reaction that we're doing, and we just track it over time, measure the concentration, and see what's happening over time. A CSTR, on the other hand, It's all, in some way it's simple in that you've got the continuous stirring, you've got the inputs, the outputs, some reaction going on, and that's kind of that. In this case, though, our accumulation rate, we had in that volume dc dt. Here, like I mentioned earlier, if we have a Q coming in and a C naught, and there is potential we could have multiple Qs, so we'd have to add each input in that way. So if we had a Q1 and a Q2 or something, we'd add those, right? This is the input rate, so if we have more than one input, we add more than one input. So anyway, we have, in this case, that would be Q C naught minus Q C plus whatever reactions are happening in that volume. I'm just going to write this as reaction now. Again, we'll come back to this next time. That could be a decay reaction, in which case we'd have a minus whatever, and that would be that. If we're at steady state meaning we have no net accumulation of C, this dc dt goes to 0, and then the mass balance becomes 0 equals Q C naught minus QC plus the reactions. So another thing we can do if we do have steady state, we can take a look and say, oh, well, the other thing we can say is that the inputs are equal to the outputs, and the inputs and anything adding stuff into the system, any growth rates, are equal to the outputs and anything decaying the stuff. So if you do get confused ever about how the reactions might fit in, and you're looking at a system that's at steady state, one thing you can do is say the inputs, Q C naught, plus any growth reactions are going to be equal to the QC leaving plus the decay reactions, because we have a balance there of the rate at which stuff is being added or produced is going to be equal to the rate at which stuff's being removed or decayed, destroyed. Okay? For the plug flow reactor, it's both simple, and if you wanted to look at it in a different manner, it's a bit complicated. The simple way is to treat each of these plugs, like I mentioned earlier, like one individual batch reactor. But it's a batch reactor that's going to travel through the pipe, through the reactor. So in the previous case, for the batch reactor, we have it on a basis of time, and we'll end up finding that really what we're looking at is some reaction for time t. Okay? So really the controlling variable there is how long did I let it sit in the water stirring and reacting. Okay? So it's some amount of time is what's important there. For the plug flow reactor, it's very similar in that each plug is acting like a batch reactor. So I'm going to say the plug is basically equal to a batch reactor. And as we'll see when we do the math later, the difference here is the time is equal to the theta, or in this case, the tau. They just wrote it tau, I'm writing it theta. I'm meaning the same thing, right? So T is equal to 1 hydraulic retention time. That's how long the water stays in the reactor. That's our design criteria for a plug flow reactor, because that's how much time this little batch of water spends going through the system, okay? So this is based on that assumption that it's perfectly mixed inside this infinitely small little plug, but not mixing with its neighbors. And so we just have that little plug, and the reaction's happening in that plug, and that's that. So in this case, our accumulation rate, again, in the volume of that plug, so let me back up a step. If we take a look at what happens in this reactor, if we're considering this little plug as a batch reactor, the system as a whole could be at steady state, right? There's some amount of concentration in there. There's stuff coming in, there's stuff leaving. There's stuff reacting in these little plugs. We could have steady state, but if we're just looking at what's happening inside that plug, it's like a batch reactor, so it can't be at steady state if there's a reaction. If there's a reaction inside that plug, there's no inputs or outputs. It's just the accumulation in that plug is whatever's reacting. So inside that plug, it's not at steady state if there's a reaction. Inside the whole system, there might be, because we have, obviously, stuff flowing in, Q, C naught, and stuff flowing out, Q and C. But we can know everything about the system just by treating it as if we have this little batch reactor on a conveyor belt. This little batch reactor goes through the plug flow reactor, goes on the conveyor belt, and when it dumps out the other side, that's going to be our concentration, whatever happened in that little batch. So whatever's coming out here is described as if it was a plug flow, as if it was a batch reactor, just spending some amount of time in there, and that time is equal to that hydraulic resonance time. Okay, does that kind of make some sense? Okay, great. And we'll look at this again with more detail about adding the reaction terms in here next time. Want to have plenty of time to cover that. The other thing we could do to model this system is to assume that we have an infinite number of these infinitely small plugs, and they're each stationary, and water is flowing in one, from one to the next, and out of one to the next. So we could model it mathematically like that, where we have some Q, C naught, and then same Q is going to go through, then we have C1 and C2, and each of them is acting like a CSTR. So we have an infinite number of CSTRs, so infinite CSTRs. This is another way to mathematically model it, and it turns out that the math becomes the same thing. So the math gets us to the same answer both ways. This one's just more complicated. It's kind of interesting that we could also conceptualize it in that manner. So I'm just going to say same math result. Okay, so I'm going to separate those two. All right, so don't worry too much about that. I think it's interesting. You can mathematically look at it that way. We will probably take a look at a non-infinite number of reactors in series and what that means for how you mathematically understand what's happening if you pass through two different reactors. How can you approach that type of a question? Oops. Okay, so I think that's all I have for today. Thought I had this loaded up. One moment. I don't have a particular Kahoot ready for you, so we're just going to do attendance real quick. Okay, so your homework assignment, first one is due in class on Thursday. I will, by Thursday evening, I'll post your second one, and then you'll have a week to do that, and then that's our exam review, and then we'll have our first exam. So that's the schedule so far. If you have any issues, please let me know. Please log in with your 89 number. I'm not gonna catch it if you use your name. I think there's a way to log out and back in. If you can't figure that out, just shoot me an email. Yeah, please print it out and bring it to class unless you're unable to come to class if you're sick or something. Then you can submit it online, and please do as a PDF, one PDF preferably. But yeah, I prefer it in class so I can mark them by hand and all that. Simplifies things a little bit for me. We'll go over both homework assignments as kind of part of our exam review. I'll try to give time for any other questions or make sure that I can address them along the way. Yeah.
So what day is going to be our first exam?
It's in the updated syllabus. I think it's October 5th, 2 weeks from today.
I just checked it like the other week, or whenever I guess it was updated. So it didn't know if that was correct.
Yeah, it should be correct now. It is in October for sure. If it still says the 30th, please let me know and I'll fix that. Okay. All right. Anybody need a moment to get in? The people online should say hi to me because I appreciate it if you say hi when you're online. So it's not just 12 viewers and I see nothing else. All right, are you here? Wrong answers only. All right, so we will pick up with reactions in these reactors next time.
I'm Ann. I was out all last week. But can we work it on loose leaf for the homework, or do you want us to print actual homework and do it on there?
Loose leaf is fine as long as you're clearly marking which
it's
problem
gonna
you're
be
working
numbers.
on. Yeah, that's no problem.
Perfect. Thank you.
My times were screwed up today, so for some reason I thought it was at 4 and I'm at 3, so I got here 5 minutes ago.
That's no problem.
Did you record the lecture?
Yeah, it's live right now.
Okay,
So
cool.
you'll be able to see it. I will post it eventually, but you can go on Twitch and just see it immediately right there.
Thank you.
Mhm. So guys, for you all that are still online, do I need to add time to the Kahoots? I know there's some delay here. Do I need to add some time for you guys to participate properly? I've been meaning to ask you and to think about that. So I think it's a 5 to 10 second delay, but it might be more like 20 seconds from the time that I do something in class and you guys do something here. If you did get kicked off, again, please send me an email. Let me know you were here. And if you're still around, please let me know if you need more time on these Kahoots because of the time lag. Okay. All right, so you need a little bit more time at the start too then, before I click start on the Kahoot. So if it sounds like a little more time at the front and a little more time on the questions themselves. All right, sorry about that, but please feel free to email me if you were there and didn't get in. I want to give you credit for being here. Happy to answer your questions whenever you do ask them. I should be aware if you do type them during class, by the way. Okay, thank you. All right, you guys have a good day. Okay. Yeah, just send me an email. All right. We'll see you guys on Thursday.